In this video, we're going to walk through a solution for a practice problem that connects equilibrium constants to cell potentials. And we're looking at a reaction under standard conditions that's between copper and hydrogen cations. So I'm going to write out the equations that we need for this. We don't have any information other than the chemical reaction and temperature and standard conditions. So we're probably going to need to know our cell potential since this is a redox reaction. So the standard cell potential will be equal to the standard cell potential of the cathode minus the standard cell potential of the anode. Or you could say the standard potential of the reduction plus the standard potential of the oxidation. And then you have to be sure not to use a reduction potential for oxidation. I have a preference for this one and always use the reminder that my oxidation occurs at my anode and my reduction occurs at my cathode. But either one will get you the same answer. So looking at my equation, I'm seeing copper solid go to copper plus 2. So my copper ion is being oxidized. And my reduction is my H plus. So looking up my standard cell potentials from just my standard table, the reduction potential for copper plus 2 going to copper is going to be equal to plus 0.34 volts. And the reduction potential for my hydrogen ion is going to be equal to 0 volts. That's my standard hydrogen potential. So that's kind of simple. Now, the number of electrons that are being transferred here, I need to find as well. It's going to, or let me find the cell potential first, and then we'll do that. I'm jumping ahead. I got excited. So that cell potential is equal to my cathode, which is 0, minus my anode, which is 0.34, giving me a potential of negative 0.34 volts. So now I'm going to determine the number of moles of electrons. My copper is going from copper to copper plus 2, so it's a 2 electron difference. And my hydrogens are each undergoing a 1 electron difference, but there's 2 of them. So I'll have 2 moles of electrons that participate in a balanced redox reaction. All right, now with these pieces of information, I'm going to use the equation that the standard cell potential is equal to 0.0592 volts divided by that number of moles in the balanced equation, log of K. So I am going to calculate K for the reaction from my cell potential. And at this point, it's really about plugging in. So that cell potential is that negative 0.34 volts. That's equal to 0.0592 volts divided by 2. That's my moles of electrons, log of K. So now as I go through and solve this, I'm going to first get K isolated, or log of K. So log of K is going to be equal to negative 0.34 volts times 2 moles of electrons, all divided by that 0.0592. Which is going to be equal to about negative 11.49. It kind of goes on. So that means to isolate K, it's going to be equal to 10 to that negative 11.49, which will give me a value of 3.3 times 10 to the negative 12th. So I have an equilibrium constant that favors reactants.